Okay, so last time we started out by pointing out how induced maps relate to homotopies. All right, so if you have a homotopy of maps between x and y, then you have induced maps from the fundamental group. Right, you have your initial map, and that maps you with base point phi0 of x naught. And you have the final map, which maps you into the fundamental group with base point phi1 of x naught. So they can't quite be equal on the nose in general because the base point has changed. But it turns out that the relation is as simple as you could hope. Namely, this homotopy is also giving you, by looking at the endpoints, or rather the image of x naught, it's giving you a path between phi1 of x naught and phi naught of x naught. And for any path joining base points, we get an isomorphism of fundamental groups. And it turns out that these two induced maps are related by that isomorphism. Right? So it's as easy as you could hope for. So in particular, if you have a homotopy equivalence, then the induced map is an isomorphism. Okay, so previously we had proven it for homeomorphisms, but we noticed that since we're only talking about homotopy classes, we really should expect it for a homotopy equivalence, and it works. Then we talked about the Van Kampen theorem as a great way of computing fundamental groups. Right? And for the case of an open cover by two sets, we saw that if you can write X as a union with A, B, and A intersect B open and path connected, then so one way of writing this is in terms of diagrams. So let's say that C is the intersection. Then if X is, let's say, determined by this diagram, in that it's what you get if you take A and B and just identify points in A and B if they come from the same point in C, then if this is such a diagram for the sets, then the corresponding diagram for the fundamental groups also has this property. That is, this group is defined by this diagram, and that it's the largest thing, the largest group containing the fundamental group of A and the fundamental group of B, with the property that any element of the fundamental group of C gets identified in both of these groups. Right? So, i.e., pi1 of x is equal to the free product of these two, where you mod out by a normal subgroup and the normal subgroup of this generated by IA star F I B star F inverse, where this is going to be IA, this is going to be IB. So these are the induced maps. And this is a class in pi1 of C. And of course, to make the base points work out, you just pick a base point inside A intersect B, and you use that base point for all of these fundamental groups. Okay. So we saw lots of examples, or several examples, of using the Van Kampen theorem with two sets to compute a fundamental group. Right? In particular, for cell complexes, this works very well. Right? If X is a cell complex, then the inclusion of the one skeleton induces an injective map, sorry, surjective map. Right, so all of your generators of the fundamental group come from the one skeleton, and the inclusion of the two skeleton induces an isomorphism. Right, and I was about to explain how this works in a slightly more general context when we ran out of time. Questions on last time? Right. In particular, of course, it's important that the statement of Van Kampen be clear.
I guess I just have a question. I don't know if this is, I mean, maybe it's just going to get answered really quickly, but we said that we talked about the one skeleton and the two skeleton, and they tell us about like the generators, and I forget what the two
Relations.
The relations.
Uh-huh.
Are we going to prove that that's
Yes.
true?
Well, yeah, we're about to prove a statement that would imply that. Yeah.
Was that the statement that we stated at the end of class?
Well, we didn't quite get around to stating it,
Okay.
but yes.
Okay.
Uh-huh.
All right, that's my question.
Okay, great. Any other questions on last time? Okay, great. So, let's consider something a little more general. Let's assume that a space Y is obtained from a space X by attaching some two cells. All right, so indexed by alpha along maps phi alpha. So remember, every two cell is just a two-dimensional ball, and you attach it by a map from the boundary of that ball into your space. Right? So the boundary of the ball is just circle, and so we need a map into X. Okay, so if you like, here's X. Phi alpha tells you where to put a circle, and then you obtain Y by attaching, filling in that circle with a disk. So Y, so this would be Y. This would be X, and this is the map you've attached by, yes?
So if phi sub alpha has codomain X, that implies that these two cells are only glued to X and not also to one another?
They're glued to X. That's right. So yeah, you have it. In this case, if you're constructing a cell complex, then the two skeleton is obtained by maps into the one skeleton. Yeah. Okay, so that's the picture of what we're doing, and we want to know what happens to the fundamental group. So when you look at this this loop inside X, it might be homotopically trivial in X, but it might not be. Right? I don't know what's going on inside the circle inside X, but definitely once I've glued on the northern hemisphere over it, then this loop is trivial in Y, right? Because I can just take the loop and homotope it up to the North Pole, right? So the images of these guys may or may not be null homotopic in X, but they're certainly going to be null homotopic in Y, right? Yes?
I just want to make sure I understand what's going on in the picture. So the northern hemisphere, that's the 2-cell.
That's right. That's right. So if you like, the 2-cell is just a disk, right? And then you have X, and phi alpha is going to be the one that says take this boundary circle and map it to this loop, right? That's phi alpha from the circle, from the boundary to here,
Okay, thank you.
right? Mm-hmm. Yeah. So I mean, you could think that we have a 2-hole torus, and I take a loop like this, and I attach my cell like that. So what I'm doing is I'm filling this in with a little membrane, say in the center of the hole. So it's like you have a donut, but instead of having a hole you could put your finger through, that hole just has a little trampoline that you can bounce your finger off of, right? And so this loop becomes trivial after I glue in that little trampoline, because I can just contract it to the center. Right, I filled in the hole. Okay, so everybody happy with attaching? Okay, so these are going to become trivial in the fundamental group of Y, and the claim is that basically that's all that's going to happen. So, fix a point in X, so we can talk about the fundamental group. Let's identify each of these with a map from the interval, because that's how we've been talking about elements of the fundamental group, but just in the obvious way, just take phi alpha of cosine of 2 pi t, sine of 2 pi t. All right, so just parameterize the circle with the interval and then take phi alpha to be that. Then choose a path. Call it gamma alpha from our base point to the image of the base point of, to the image of 0 after you've reparameterized this way. And then you get a loop by concatenating like this. This is a loop in X based at X naught.
Sorry, what's inside phi alpha of 0? Is that what this?
Phi alpha of 0, yeah. So after you've parameterized by the interval, so just wherever you send 0. Or if you like up here, it's wherever you were sending the base point 1, 0. Okay, and let n be the normal subgroup of pi 1 x x naught generated by these loops. Okay, so like we were saying, each of these loops becomes null homotopic in Y, Gesundheit. But we want to talk about that in the fundamental group of X, so we just need them to be based at X naught. So we do the usual thing of putting a path in to make it start and end at X naught. And now we have elements of the fundamental group. And the claim is that attaching these just kills n. Okay, and it doesn't do anything else to the fundamental group. Yes?
So when you say the normal subgroup generated by the loops,
Yes.
so is that just then the smallest normal subgroup that contains them?
Correct.
Because now pardon me for forgetting group theory, is that necessarily the subgroup generated by them?
No.
Okay, that's what I thought.
Yeah.
That's what I thought.
Uh-huh. Okay. Okay, so let's state that. Position, so include x into y. And the claim is that this induces a surjection with kernel n. So pi 1 of y, y naught is pi 1 of x, x naught mod out by n. Okay. So what we're going to do is replace y with an equivalent space that makes it easier to see this. Right? So let z be. So let's do a picture first, and then we'll try to describe what we're doing. So here's our point x naught. Here's one of the loops where we're gluing, and here's another one. So in y, each of these becomes a little bubble. And we have some path going to the base point over here, and we have some path going to the base point over here, right, to make these elements of the fundamental group based at x naught. Right? So what we're going to do is we're going to take this path, and we're going to thicken it up to a little strip, right? So a little ribbon, if you like. And we're going to attach the endpoint over here onto that bubble, right? So it's just a little piece sticking up over there. And same thing over here. But the
So these lines are lying above.
these are lying above. So yes, this is a little ribbon whose edge is where the path was, and whose upper edge is not attached to anything. Right? So we're just taking each of these paths and thickening it up a little bit. Right? This, of course, is a homotopy equivalent to y, because you can just push this ribbon down to its edge. Right? So y is a deformation retract of z. Right? But it gives us a little space to play with. So let's see, i.e. the space obtained from y by attaching a strip along each gamma alpha with right ends attached to the 2-cell E alpha 2, and the left ends of the different strips mutually identified. Okay, so here above x naught, there's just a single little interval, right, from all of the different strips, the same interval. Okay, so in each 2-cell, choose a point y alpha disjoint from x and the strip. Right, so just pick the north pole of each one of these. So this would be the point y alpha here, and this y alpha prime over here. Okay, so just to pick points and consider the cover z minus the union of these points, and b is z minus x. Okay. So by putting in this little strip, when we remove x, we still have, well, most of the strip, so they're still connected. Okay, so let's stare at these sets. If I have said, and I remove the North Pole from every hemisphere, well, once you remove the North Pole from a hemisphere, the hemisphere retracts down to the equator, right? So each of these bubbles goes down to the loop it started on, right? Each of these strips you can push down into x. So A is deform retracts onto x. Right, so up to homotopy, A is the same as x. Whereas B is contractible. Right, because every hemisphere, right, contracts to the North Pole. Right, and so you can contract all of this down to, say, that little piece of the strip, and then all of the strips, you can take them back to the one living above x naught, and then you can just push that down to x naught itself, or to any point on it. And so you're just left with the point. Right, so B is contractible. The intersection is remove x and remove these points from the hemispheres, right? Well, if you remove a point from a hemisphere, then it's no longer contractible. Now it's really just the equator, right? So now we've just ended up with these circles, right, joined together by points, by a path to a common point, right? So that's just a bouquet of circles, right? Because you can just retract that path so that they just have a point in common. But in particular, this is path connected. So Van Kampen applies. And it tells us that pi1 of z is pi1 of a, free product with pi1 of b, but that's trivial, mod out by the image of pi1 of a intersect b in pi1 of a. Okay, but that's pi1 of x, and then you're modding out by the normal subgroup generated by what's left when you mod these out. So you just have, for each circle, you have the path gamma alpha followed by the attaching map, the attaching loop, and then followed by gamma alpha back. Right? So this is precisely what we wanted. This is generated by gamma alpha, gamma alpha bar, as required. Okay.
Can you explain that again?
Yeah, so this is what we were saying, that if you remove x and you remove the North Pole from each hemisphere, then each hemisphere just retracts back to this loop, right, to an equator. And you can retract this strip down to just a path to anything lying above x naught, because we removed x naught, but anything on that interval, right? And so all that's left is, well, the path gamma alpha, then this loop phi alpha, and then going back. Okay, so that is how Van Kampen lets you compute the fundamental group of cell complexes just by looking at the one skeleton and the two skeleton. Okay?
What is the why not in the proposition?
Oh, why not? Why not is x naught. Thanks. as it has to be, right? Because the inclusion just maps x naught to x naught. Okay. Perfect. So that's the application of Van Kampen. And so now it's time for us to prove Van Kampen. Okay. So here is a more general. Yes.
So what we've just gotten at the end of this proof is the fundamental group of Z.
Yes.
Do we then want an additional step, some sort of deformation or traction, to show that that's the same as the fundamental group of Y?
Right. So I guess I didn't write it down, but I did say that that said has Y as a deformation retract.
Okay.
Yeah. So, but indeed, as you say, you just take those strips, push them down until they're living on X again, and then you have Y.
Okay.
Yeah. Thank you. Okay, so here is the Van Kampen theorem, a little more general. So suppose that A alpha is a collection of open, path-connected subsets that covers X with some base point contained in all of them. So let J alpha be the inclusion of A alpha into X, and for each pair, let I alpha beta be the inclusion of the intersection of A alpha, and A beta into A alpha. Right? So the order matters. Okay, so let phi go from the free product of all of the fundamental groups into the fundamental group. Let's not be the extension of the J alpha star. Right, so every one of these inclusions induces a map of fundamental groups, right? Maps the fundamental group of A alpha into the fundamental group of X. We saw that the free product, its defining property is that every time you have a homomorphism from each of the constituent groups into some fixed subgroup, then there is an extension of that to a homomorphism from the free product into that subgroup. Right?
What are the subscripts on the last?
Pi 1 of XX naught.
No,
Oh,
yeah.
alpha star. Yeah, so the induced maps from the J alphas. Okay. So first, if each pairwise intersection is path connected, then phi is a surjection. And then if each triple intersection is path connected, then the kernel of phi is the smallest normal subgroup containing I alpha beta star of the class of F times I beta alpha star of the class of F inverse. For all alpha, beta, and class of F inside the fundamental group of A alpha intersect A beta. Okay, so it's the same story we had before. The kernel is going to be all of the loops in the intersection should be identified. You're identifying in here the element in pi1 A alpha and the element in pi1 A beta that you get from a single loop in A alpha intersect A beta. Okay? So that's the statement. Questions on the statement? Yes?
So when there are only 2 of the A alphas, is this the same exact statement as Van Kampen?
It is. That's the one we saw before, yeah. Because then this is trivially true as long if this is true. This is the product in the normal in the free product, right? So each of these, right? I alpha beta goes from A alpha intersect A beta into A alpha. So this is an element in here for the A alpha, and this is an element in here for the A beta. And so in here, in principle, there's no way of simplifying this when they sit together. Sorry? It's a word. It's a word, yeah. And it's a word with each element in a different group. So there's no relation in here a priori. So what we're saying is when you map across here, those are the relations that are added. Okay? Okay, great. Wonderful. So let's prove this, starting with part 1. So we want to show that phi is a surjection, right? So we want to take an element here, and we want to show that it came from somebody over here. Right? So given a loop in X based at X naught. Okay, I want to write this as a bunch of loops, each one inside a single A alpha, right? Well, the A alphas cover X. So I can find a partition of the interval right, a finite partition such that F maps ti plus 1 into a single A alpha. Right. So I have a finite cover. The inverse image of each of these open sets is an open subset of the interval.
Wait, where does it say that there are only finitely many A alphas?
It doesn't. There could be infinitely many. But here, by compactness of the interval, I can find a finite partition that does this.
Okay.
Right? So if you like the inverse image of the A alphas, that's an open cover of the interval. Right? And so there is a finite subcover.
Okay.
Okay, I'm going to assume everybody's read the announcements by now and reclaim the board. Okay, so denote the A alpha corresponding to T I minus 1 Ti by AI. And let Fi be the restriction of F to Ti minus 1 Ti. Now, for each I, pick a path gi in a I intersect a I plus 1 from x naught to f of ti. Right? So here we're using that this intersection is path connected, and by assumption, every one of the sets contains x naught. Right? So in particular, the intersection contains x naught, and so I can pick a path from x naught to wherever it is I ended up there. Okay, so Fi is homotopic, no, actually F itself is homotopic to the loop F1 dot G1 bar, and then do G1 F2 G2 bar, and keep going until you do G whatever index I used, L minus 1 dot FL. Okay, so everything in parentheses is a loop based at x naught, right? This is homotopic to F because we know that if you do a path and then its reverse path, that's homotopic to the constant, right? So each of these pairs cancels in homotopy. So you just end up with F1 dotted with F2 and so on, and that's exactly F up to reparameterization.
And presumably because we're working with paths here, when we say homotopic, we actually mean path homotopic?
That's right. Yes, thank you. So yeah, it's path homotopic to this loop. Right? But also, note that this guy stays inside A1, this guy stays inside A2, and so on. Right? Each of these loops stays inside a single A alpha. Right, so, well, actually in. Okay, so since each factor stays in a single AI, this shows that the class of F is in the image of phi. Right? So just consider this factorization as a word in the free product, right? Which is fine because this is in pi 1 of A1, this is in pi 1 of A2, and so on. Right? So consider that word, map it by phi, you just get this, and that's F. Okay?
When you say pi 1 of A1 and pi 1 of A2, that's always at the same base point?
That's right, yeah. Yeah, so so we have x naught living in all of the A alphas. So throughout the whole proof, the base point is x naught. Okay, so we're going to call this a, okay, that proves part 1. We're going to call this decomposition of a loop F a factorization. Right? So refer to, so let's say, by a factorization, of f, we mean a word in the free product possibly unreduced. All right, so over here, just a moment. Over here, there was no guarantee that AI plus 1 was different from AI. So I might have repeated, and I'm OK with that. Yes?
So first off, for part 1, we have the assumption that the intersection of two A's is path connected. Just to make sure I'm getting this right, we needed that to get G sub I?
That's right.
Okay. In this factorization, is it possible that one of the A's is repeated not consecutively as well?
Sure. Yeah, yeah.
And then we couldn't necessarily reduce it?
That's right.
Okay.
Very good. Any other questions on the proof of part 1? OK. So by a factorization, we mean a word like that gets mapped by phi f. And we're going to say that two factorizations are equivalent if you can get to one from the other by a finite sequence of two steps, two allowable steps. So on the one hand, they should be equivalent if they have the same reduction. So we're going to allow you to combine fi and fi plus 1 to fi dot fi plus 1 if they are elements of the same pi 1a alpha. OK, so nothing special there. It just means that they were elements, the same elements of the free product. But then the other move you're allowed to do is if fi is in pi 1 of a alpha is in the image, well, I guess it should be, well, let's stick with alpha. It's in the image of of the fundamental group of a alpha intersect a beta, then we may consider it as an element of pi 1 a beta. OK? So the other step is when you're looking at a factorization, so you have each of these loops, and they live inside some AI, right? The AI was given to you because you chose one of the open sets that this maps into, right? But maybe this loop is actually in the image of AI intersect some other A beta, right? Then you're allowed to think of this word as equivalent to what you would have gotten if you considered this as living inside the other open set. Yes?
So do we want a third step where we can split something apart into two copies of the same AI?
Well, yeah, I mean, you're allowed to do these steps or their inverses. Or if you like, you could do the step to both words, right, before you get something the same. Yeah.
Okay.
But yes, that would certainly be considered equivalent. OK, so the first step, as we mentioned, doesn't change the class of your factored word in your factorization as a word in the free product. And the second one, so the second step, does not change the class of the word in, let's call it Q for quotient, what you get from the free product by modding out by n. Because that's exactly what n is. It's given a word, given a letter that's in either pi 1 of a alpha or pi 1 of a beta, you consider them equivalent. You can consider it as an element of a alpha or an element of a beta, and you get the same. OK? So now what we have to do is show that any two factorizations of a given loop in X are equivalent. Okay? So we have these two steps we're allowed to do. And we have to show that if you give me two factorizations of a given word, then by a finite number of those steps, I can get from one factorization to the other one. OK, so suppose that a given f has two factorizations. So we're going to write it as f1 through fl and f1 prime to fk prime. Okay. With each fi or fi prime a loop in some a alpha. OK? Different a alpha for each one. OK, so we want to do the same thing we did with the single loop. We want to use compactness to break this into pieces that get mapped into a single a alpha, right? And we want to do that to get from one factorization to the other. Okay? So first, we do have a homotopy between them in X, because they do represent the same class in the fundamental group of X. Right? So there is a path homotopy. Take capital F from 0, 1 cross 0, 1 to X such that f of 0, 1 dot t is equal to f1 dot fl at t, and f of 1 comma t is equal to f1 prime dot fk prime evaluated at t. Right, so the path at the left endpoint of the first interval is just the concatenation of this factorization. And at the right endpoint of this interval, you just get the path given by concatenating these guys. OK, so by the same compactness argument, we can partition each interval So you have S0 less than S1 to S M, and then you have T0, T1 to Tn. So that F maps each subinterval Si minus 1 Si cross Tj minus 1 Tj is in a single A alpha. Okay, so same reasoning. That's an open cover of X. You pull it back by this continuous map. You get an open cover of this compact set. So there's a finite subcover. So you can do this.
So like the end indices on the S and T, are those the same?
No, I and J. So it's for every subinterval here cross every subinterval here.
Okay.
You land inside some A alpha.
The partition of the S's and the T's.
Right, they're not the same.
So are those? Sorry, I can't read it.
It's M and N.
Okay.
Yes. Right. So, right, we've ended up with some grid, and F maps this to X. But it has the property that every little square gets mapped into a single open set. Okay, perfect. So our hypothesis, remember, is that the triple intersection of open sets is path connected, right? Yes?
So is Ln, M, and Kn and R necessarily the same? Or?
No. No, all of those letters represent potentially different natural numbers. Yeah. So, oh, right. So you might have, you're saying, well, how do I know that I have the same number of elements here or elements there, given that I've put the same number of squares at the bottom or the top, right? Well, feel free to fill in with constant loops to make them the same length. Right, that won't change anything. Okay, so I want to change things a little bit because our hypothesis is that triple intersections are path connected. So we're going to, okay, triple intersections, and what I don't like about the current setup is that in our grid, every vertex in the interior is touching 4 little rectangles. So it's involved with 4 open sets, and I only have a hypothesis for 3 open sets. So we're just going to shift the squares a little bit so that vertices are only going to intersect 3 rectangles. Right? So by small perturbation, so I want to keep the lines of the first row and the last row the same because I want to end up with the first factorization on the bottom and the final factorization, the second factorization on the top, right? So I don't want to change these intervals. Right, I should have said. The partition, we can, by a subpartition, make sure that each of the Fi's corresponds to, perhaps a pair or more contiguous down here, and all of the fi primes correspond to some contiguous set up here, right? So that the path, if you follow the bottom with these divisions, gives you a factorization equivalent to the one with the fi's, and the one on top gives you a factorization equivalent to the one with the fi primes. And then you're just going to move these lines a little bit so that the vertices only involve 3 squares. Right? And by making this change small, you still get that you're mapping each rectangle into a single open set. So by small perturbation, each vertex intersects at most 3 subrectangles. Okay, so and let's assume that you have at least 3 rows, so that this happens without changing the first row and the last row. Okay, so let's number these. From bottom left upwards. Well, so right, then up, right and up. So it doesn't really matter too much, but let's go like this. And this is n times n. Okay, then for each I, so for each index, say I, between 0 and m, let gamma I be the word obtained by f restricted to the path from left to right that separates the first I boxes. Good night. Okay, so let's say we're like this. Then 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so gamma 0 would be take this bottom line and restrict f to that. Right? So gamma 0 is f restricted to the bottom edge. Right? Gamma 4 would be, I want a path that starts at the left side, ends at the right side, and separates the first 4 boxes from the rest. So you're going to go like this, like that. Right? So make that curly. Gamma 4 is f restricted to the curly path. Right? And gamma mn, so 9 in this case, would be just go along the top. F restricted to the top edge. Okay? Now, because f is a path homotopy, it sends all of the left edge to x0 and all of the right edge to x0. All right. So each of these gammas is a word, an allowable word. Right? It is made up of loops based at x0. Each little path that you follow, well, okay, so we're going to make each little path that you follow a loop in a moment. But it's certainly giving us a factorization of f into a concatenation of paths. Right? And each path stays inside a single A alpha. Okay. Okay, so each vertex lies in, at most, 3 rectangles, which corresponds to 3 open sets. And I'd say A alpha, A beta, A gamma. So let G be a path in A alpha intersect A beta intersect A gamma, joining f of the vertex with x naught. Right? So just like we did when we had a single path and we wanted to turn it into a bunch of loops based at x naught, with each loop staying inside a single A alpha intersect A beta. Now we're going to do the same thing, but we're going to make sure that each vertex, so there's an A1, an A2, and an A5, and we want this path to stay inside A1 and A2 and A5. Right? Okay, so by so we can factor each gamma I into a word with each letter corresponding to f restricted to an edge in the grid. With each letter corresponding to this, joined to x naught using the path G for the first vertex and the second vertex. Right? So, for example, over here, the curly path, that gave us a loop in x, and we want to factor it. We want to factor it with one factor per edge that you followed, right? And so we know that each of these edges stays inside some A alpha, right? But it might not end at x naught, so it doesn't give us a loop, right? But we have a path G that will follow to get to x naught, and then we'll follow it back to, actually, I guess it starts at, yes, we follow it to get to x naught, and then we follow it back to be back where we would have ended. Then we do the next edge, right? And we do the same thing. We want it to start at x naught, so we use the appropriate G. And then we want it to end at x naught, so we go back along the other G, right? OK? So this gives us factorization. So for each index between 0 and mn, we have different factorizations. They all correspond to the same loop in x because, well, there's the homotopy between them, right? So we have mn different factorizations of the same loop in x. They start with the factorization at the fi's. They end with the factorization at the fi prime. So it's enough to notice that these are all equivalent. Okay? So So in this way, we have a sequence of factorizations of f starting with the first one and ending right. Of course, modulo adding some constant loops to make sure that they have the same ends, and perhaps to make sure that they have the same partitions. But anyway, up to small modifications, certainly equivalent, then we're going from this one to that one, and we just need to make sure that we didn't change equivalence classes in between. Okay. Fantastic. Okay, so the only thing left to notice is that these are equivalent. These are all equivalent since passing from gamma I to gamma I plus 1. So if you have gamma 4, right, which followed this curly path, and now you want to go to gamma 5, which follows this hashed path, then the only difference is in square 5, right? And square 5 gets mapped into a single AI, right? So you just do a homotopy inside AI to get from this factorization to that factorization.
And you don't have to worry about connecting this because the corner is no part where it's touching 3.
That's right.
You know the time.
Exactly. Yes. It just involves a path homotopy in a single A alpha. Okay? So that proves Van Kampen. Okay, excellent. So we now have two ways of computing fundamental groups. For the circle, we did this thing with a cover. So we showed that you give me a path on the circle, I can lift it to a path on the real line. And then just by seeing what happened to the endpoint, we were able to see that you had the integers. And then all of the other computations have been with this Van Kampen. So you pick a cover, and then you see how the fundamental group of the different elements of the covers fit together to give you the fundamental group of the whole space. So there are two questions you could ask. First, can you get the fundamental group of the circle by a cover? Right? So of course, Van Kampen, the way we've stated it, won't work. Because if you cover the circle, say by just inflating half circles, then the intersection is not connected. Right? So Van Kampen is not going to work. So we're not going to do this, but let me tell you that there is a version of Van Kampen's theorem for groupoids. Right? So remember, the fundamental groupoid of a space was defined to be just path homotopy equivalence classes in the space. So it turns out that there is a Van Kampen for groupoids, and it works with, you can pick some base points, but it doesn't have to be a single base point. You can pick multiple base points, and then it's path homotopy classes of paths that go from somebody in your base points to somebody else in your base points, right? So that allows you to have disconnected things. And then the version that we wrote for two open sets of a push out of sets gives you a push out of groups. That statement is true for groupoids once you make sense of push out of groupoids. So it turns out that you get the push out of the groupoids, and you can show that's the integers, right? So if you want to see that, there's a book called something like Topology and Groupoids by Brown, and he does this. In fact, I think the theorem is due to him. So that's the first thing. The other thing you could ask is, OK, can you compute other fundamental groups using covers? Right? And so that's the next topic we're going to cover, is covering spaces. And it turns out that there's a big relation between different covers of a space and different subgroups of the fundamental group, very much like Galois theory, with different extensions of fields and subgroups of the Galois group.